Hi, welcome to module 31 of week 6. In this module we are still going to look at state machines and we are going to learn something very fundamental to state machines, which is called state minimization. So before we look at state minimization, I will show you a design example first, which is another very interesting example and a very simple example to understand. I will show that and then we will talk about state minimization. So let us look at this design example. So this is called a tail light controller. So if you drive a car and we are going to design a state machine which are going to control the tail lights of a car. So we are going to have a car which has 3 lights on left side and 3 lights on the right side. We are going to control it to turn signal, which means if I want to do a left turn, I want to show that I am turning left. If I want to do a right turn, I want to show that it is turning right, or I may have a hazard. So hazard means there is some problem in my car, so I want to press a button and say that there is some panic, and anyone who is behind me should understand that there is these lights blinking, which means there is a problem in the car. So these are controlled by, let us say, left, right and hazard signals. So from a car's control point of view, when I drive, so if I press down the indicator, I want to indicate left, if I press up, I want it to indicate right, and then if I press a button, I wanted to press this hazard. So let us assume that there are 3 inputs, left, right and hazard, which are given to this circuit, and I want to control the tail lights accordingly. So let us see what the tail lights are. The tail lights are going to have some interesting thing. So there are 3 inputs, left, right and hazard, and I am going to have 6 outputs. LC, LB, LA are 3 left side indicator lights, and RA, RB, RC are right side indicator lights, and the car I have is something like this. So this is my car here. I have 3 lights on the left side and 3 lights on the right side, and if I press left, then what I want is, so you see the thing that is happening here. I want to start from the leftmost bulb, then turn on this one, then turn on this one, and come back and turn off all of them. This is what I want for left. For the right, similarly, I want to start from here, then turn on this one, and then come back and then keep doing this over and over. Let us say that is the thing that I want. So this is not a typical signal that you will see in cars. So in most cars you will see just one light on the left side which keeps blinking and one light on the right side which keeps blinking, but this is a very simple example to give you how to design a controller. And if it is a hazard signal, what I want is all the lights should blink and go off. It should keep blinking as long as the hazard is on. So as long as I keep, if I have left indicator on, then I want this bulb and this bulb to glow, then all of them goes off, then again this bulb glows, and all of them goes off, and so on. This keeps happening forever until I remove the left indicator. Similarly for right indicator, and if I want to indicate hazard, I press hazard equals 1. If I put hazard equals 1, all these lights should all blink, so which means it should go to 1, go to 0, go to 1, go to 0 all together. So let us say this is the circuit that I want to design. So let us design a state machine to do that. So the ideal state, we will mark it as all zeros. The ideal state is when you are driving, there are no conditions, you are going straight, you do not have a problem in the car, so all the outputs are 0. So LC, LB, LA are the 3 left indicator bulbs, and RA, RB, RC are the right indicator bulbs. All of them indicate 0, and if all the inputs are 0, I do not have any condition, so I will stay in the ideal state of the lights itself. The lights are not glowing. The moment I turn on the left indicator, the left indicator is turned on, means L equals 1, R equals 0 and H equals 0. The moment I do that, the first thing I want to do is turn on the bulb called LA, then turn on the bulb called LB, turn on the bulb called LC, and go back to the ideal state. So let us see this one here. I press the left indicator. The moment I press the left indicator, then the cycle that I want is L1 should glow, then in the next cycle L1 and L2 should both glow, then in the next cycle both LA, LB and LC, all three should glow. So I said L1 and L2, I am sorry, L1, L2, L3 are the state names. So at L1 I want LA to glow, at L2 I want both LA and LB to glow, and at L3 I want LA, LB, LC, all of them to glow. And I want this to happen as long as the hazard light is not turned on. Maybe I put the left indicator on, but suddenly I see a problem, immediately I press the hazard. I want to be able to take care of that. As of now, we are explicitly checking whether the hazard is 0. So if the hazard is 0, then I go to the next state from L1 to L2. If the hazard is still 0, I go to L3. If it is 1, we have to do something about it. So this is for the left indication. Similarly, I will put something for the right indicator. So as long as R is 1 and the other two are 0, I will go to the right indicator mode. In the right indicator mode, I start with RA as 1 first, then in the next cycle I will make RB as 1, in the next cycle I will also make RC as 1, and I will do this as long as the hazard signal is not turned on. And the moment I finish one cycle, no matter what happens, I come to the idle state. So I indicate, so RA turns on, RB turns on, RC turns on, and all of them go to 0. So that finishes this, and if my right indicator is still on, then I will keep doing the same cycle over and over till the right indicator is removed. So this is for the right indicator. Finally, if I want the hazard, so if the hazard light is turned on, if I press the hazard button on my car, I want all the lights to glow and they should all go to 0. So this gives you the feeling that it is blinking. So all of them turn on, all of them turn off, all of them turn on, all of them turn off, and this will keep happening as long as the hazard is 1, no matter whether I turned on the left and right indicator, right. Even if I turn on left and right indicator, as long as the hazard switch is pressed, I want this blinking action. So this blinking action will come using the state H1. Now I have to take care of several other transitions. So if I from L1 I have a XX0 transition, it means it takes care of all combinations of L and R, but H to be 0. What about the case where H is 1? So if H is 1, even from L1 I press the left indicator, but I see a problem, I immediately want to go to hazard. So that means from L1 you directly go to H1. Similarly from R1 you directly go to H1 the moment you see that there is a hazard, and you will need that from L2 also. From maybe so the left light LA came on, then LB came on, I suddenly press the hazard, maybe I was turning and then I have to brake because there is I see somebody in the front, I press the hazard light immediately. So in that case you should immediately go to hazard, and this is the overall circuit. So the overall state diagram is, if from L1 and L2 if you see that hazard gets turned on, then you want to go back to this hazard itself. But from L3 if you see a hazard, you press 1, what would happen? Let us say hazard gets turned on now, then anyway in the next cycle you come to idle, and after that you will anyway go to the hazard state. So instead of having a transition from L3 to H1 directly, we have one cycle delay to go from L3 to H1. So let us say that is the state machine, and we can do what is called state encoding. In state encoding what we do is, we for each of the states, instead of symbols H1, R1, idle and so on, we give bits. So let us see the number of states here. There are 3 states for the left, 3 states for the right and 2 states for this, that is overall 8 states. 8 states can be represented using 3 state registers or 3 flip flops in the state register. So there are 3 flip flops, which means they can take 8 different combinations. So to the idle state I am going to denote it as 0 0 0, so that some Q2, Q1, Q0, if it is all zeros it means we are in the idle state, then we have given different names to different things. So 0 0 1 here, 0 1 1 here, 0 1 0 here, 1 0 1 here, 1 1 0 here and 1 1 1 here, and for H1 we have reserved 1 0 0. So for whatever reason we have done this, and this big table tells you the state register, the state table. So the present state could be Q2, Q1, Q0, there are 3 bits, so there could be 8 different combinations, and for each of the combinations you go and write what are the conditions under which it should go to different states. So this is a much more precise or concise thing, not precise, so this is precise as well as concise. So what we have is for Q2, Q1, Q0 which is all zeros, if L or H are all zeros, then you want the next state to be idle which is all zeros, and you can get that by making D2, D1, D0 as 0. So this would mean all the lights will be 0. If left indicator is turned on and if right is off and hazard is off, then you want to turn on LA. To turn on LA, you want D0 to be 1, and you will see that at this point the outputs are all zeros even now. So because it is dictated on the state. So based on what state you are in, if you are in idle state, you always have all the lights turned off. If you are in state L1, you have LA turned on. If you are in state L2, you have both LA and LB turned on. If you are in state L3, all 3 lights are turned on. Similarly, R1, R2 and R3, you have the outputs described. So there is a much more concise representation. Instead of looking at L or H which are 3 bits and Q2, Q1, Q0 which is 3 bits, ideally you should be writing 2 power 6 or 64 lines of the truth table, the state table. Instead, we are using the don't care conditions and concisely saying I do not care about L and R as long as H is 1, and if I am in the idle state, I should go to H1 state which is the hazard state, but I will still be producing all zeros as output because when I go to the state hazard 1, it will take care of blinking, right. So at idle I am supposed to be blank, at H1 all lights glow. So this is a tail light controller. It is a very simple example that you can very quickly relate to. This table may look big, but the description is fairly simple. So you go back to the state diagram and compare it with this, you will see that the state diagram is captured in the state table. So this is obviously a lot of states. So sometimes you wonder whether you really need so many states or not. So that is where we, so you can go and derive the logic equations for it and design a circuit for it. So in this case, let us look at the logic equations D2, D1, D0. There are lots of common things. So of course these are very complicated equations. So D2 has 6 variables in this term, D0 has 6 variables in this term as well as in this term and so on. So let us assume that these are all correct as of now, let us not worry about the correctness. One thing that is happening is this term here is shared with this term here, these 2 are common terms, these 2 are common terms, or these 3 are common terms across 3 different equations, these blue ones are common, these orange ones are common and so on. So in some sense it is not that you have to spend so many gates, there are terms that you can derive and use them to derive D2, D1 and D0. You have a single circuit which does this term and share it to drive D2 and D0. Similarly, have one circuit which will do Q2, Q1 bar, Q0 bar, use that for both LA and LC and LB and so on. So this is something you can do. So you can share the gate outputs, but sometimes you wonder whether all these states are necessary or not. So to do that, we are going to look at what is called state minimization. So if you are given a state machine, you may wonder whether you have states which are not necessary or are there any redundant states. So to reduce the cost of the machine, because you can see this in this example, all these comes with the cost, right. Maybe all the states are not necessary, I do not know. So I need to have a systematic procedure by which I can take a state machine and change it to another state machine which has much simpler gates, probably fewer flip flops and so on. So to do that, so by doing that I will reduce the cost of the state machine, and to do that I need to eliminate what are called redundant states. So if 2 states do the same job, I can get rid of one of the states. So state minimization is the removal of redundant states. So to reduce the complexity of the circuit, we need to define something called equivalence between states. 2 states are said to be equivalent in a single state machine. 2 states are said to be equivalent if for each member of the set of inputs they give exactly the same output and send the circuit either to the same state or to an equivalent state. So this is a loaded definition, but we will see an example in the next slide. This will make it clear. So let us consider this state machine here. So this state machine has 1 plus 3 plus 3, 7 states, and there are some transitions given. Maybe this is a state machine that you gave to me, and I want to see if I want to, if I can minimize this state machine and I can get something equivalent, which means all the actions that you are doing here, I should be able to do that also. I should not miss out anything. So the correctness of the state machine, whatever state machine you gave, I want to do the same set of actions, except that I want to see if I can cut down the number of states. If I cut down the number of states, the number of flip flops will reduce and the complexity of the circuit will also reduce. I want to see if I can do that. So let us see how to do this. So let us say this is the original state table. So the present state is marked as 0, 1, 2, 3, 4 up to 6. On x equal to 1, this vector here tells you to which state we are going to. On x equal to 0, this vector here tells which states you are going to, and these are the corresponding outputs. If you are given this original state table, I want to see if there are equivalent states. So what is the definition of equivalent state? Two states are said to be equivalent if on the same input they give you the same output and they also move to a state which are either the same or they are equivalent. So this is a loaded definition. Let us see the definition in action now. So let us look at states 4 and 6. I am going to say that they are equivalent. Why are they equivalent? I go and look at x equal to 1 and x equal to 0. They are, so from 4 I will go to state 5 and state 0 respectively. I am also doing the same thing from state 6. State 6 on input 1 I will go to 5, on input 0 I go to 0. Not only that, the outputs that you are producing for x equal to 1 and x equal to 0 at state 4 are also the same that you produce at state 6. So this makes states 4 and 6 equivalent. So what I can then do is, these two states are doing the exact same action, I can get rid of one of them. I will get rid of the state 6, and wherever I see a transition to 6, let us see the table here, from state 5 on input 0 I am transitioning to 6, but I said 4 and 5 are 4 and 6 are equivalent. Wherever I see a 6 I will put a 4. So I will go and make that 4. So wherever I see a 6 I will put a 4. Now once more I go and check if there are things which are equivalent. So now let us look at this. It looks like 3 and 5 are going to state 5 on input 1, state 4 on input 0, because earlier it was going to 4 and 6, but now 4 and 6 we have established that they are equivalent, which means they are going to the same state on x equal to 0. They both seem to produce 1 0 as the output. So this makes state 3 and state 5 also equivalent, right. So we find out the first equivalence, based on that now 3 and 5 becomes equivalent, otherwise you cannot say that 3 and 5 are equivalent. But now we have resolved that 4 and 6 are equivalent, because of that 3 and 5 becomes equivalent, and now I can get rid of state 5 also. So you can get rid of 3 or 5, in this case I get rid of 5, and if you do that I will have to replace all the 5s with 3s. So now I have this states. I can go and check if there are any more equivalences. So I see a 3 2 here, 3 0 here, 3 4 here, 3 0 here, and a 1 0 here. So maybe states 4 and 2 could potentially be equivalent, but I go and look at the output, one is producing 0 0 as the output for 1 0 combination and another is producing 1 0. So that makes state 2 and 4 not equivalent to each other. So this leaves me with 5 states. So I can now draw a simpler state table, this is called the reduced state table. So wherever I see a 5 I will put a 3, wherever I see a 6 I will put a 4, and I get rid of the rows 5 and 6. So that gives me this state. In this example I have 5 states. So this 5 states means you still use 3 flip flops, but the logic probably reduces. So you have fewer states than what you had, and this will do exactly the same as what this state machine was doing. Whatever this state machine is doing, this state machine will do exactly the same. We have not changed the functionality of the state machine at all. So the original state diagram was this, and the current state diagram is this. So you can check whether these two are equivalent by giving in some inputs. So assume a sequence 1 0 1 0 1 1 and whatnot, you run it here and you run it here, it should So if I give you 10 bits, a sequence of 10 bits, the 10 bits will eventually take you to some state producing some output all along the way, right. The same 10 bits if I give here, it should take you through the states which are all equivalent, it should also have produced the same set of outputs. You go and check that yourself and convince yourself that this technique is correct. So in general what happens is, if there are 2 power m states in a sequential machine, we need m flip flops. So if I have 6 states is equivalent to 2 power 3 or 8, it's closest to 8, we need 3 flip flops. Reduction in the number of states may or may not reduce the number of flip flops. In the previous example, from 6 states we went to, so we had states from 0 to 6, and then we went to states from 0 to 4. So it still has 5 states, which means we need 3 flip flops. However, from 7 states, if we had gone to 3 states or 4 states, it would have cut down 1 flip flop. So there is a more methodical way of finding out the equivalences between states, and I am going to do that using what is called a implication table. So I will show that in a little while. So there is an algorithm with which you can do this, but I will show you the picture. I suggest that you go back and read the algorithm. If you get stuck somewhere with an example, you go and use this algorithm and do this yourself. I will describe the algorithm directly. Let us say this is the state machine that is given to you. So there are 4 plus 4, 8 states that are there. The states are numbered from A to G, A to H, and there are several transitions that are given. So I want to go and write an implication table for it. So the way the implication table works is as follows. So what you do in the x-axis is you put the states. So if I have 8 states, I am going to put 7 of the states, A, B, C, D, E, F, G. So I can pick any 7 states, I will put those 7 in some order here, and what I will do in the columns is, if I have A to G here, I will put B to H here, right. So we know that a state is always equivalent to itself. We do not need that at all. We do not need to check whether a state is equivalent to itself at all. A state is always equivalent to itself because it will produce the same outputs, it is going to the same states on its transitions and so on. You do not need that column. So instead what we have is, we have several states here except the last state, right, and similarly except the first state you put all the states here. So that is in the set of rows and columns. Let us now go and inspect these cells that are inside. So let us go and inspect each one of these cells. So I look at A and B. So on the rows I look at A, on the column I look at B, and I have some entry here. If I go to the state machine, on A, on a 0 input you go to H, B, on a 0 input you go to F. If you want A and B to be equivalent, then on 0 it should go to either the same state or it should go to the equivalent state. So if I want A and B to be equivalent, then H and F have to be equivalent. That is what you have here, right. Let us look at one transition from A. If on one from A goes to G, one from B goes to E, if I claim that A and B are equivalent, then by the definition of equivalence, G and E should either be the same state or they should be equivalent state. So what we are putting here is that this is, if I want A and B to be equivalent, these two conditions must be satisfied. That is what it means, right. If A has to be equivalent to B, then these two conditions should be satisfied. H should be equivalent to F and G should be equivalent to E. So let us look at this cell for instance. If D has to be equivalent to F, then B should be equivalent to E and D should be equivalent to F. This statement, D should be, for D to be equivalent to F, D to F has to be equivalent is redundant, but B to E, so B should be equivalent to E, only then D can be equivalent to F. That is the meaning of this cell. Let us look at this cell. If A has to be equivalent to H, A has to be equivalent to H on input 0, that is trivial. If this is equivalent, that is also equivalent directly, and you want G to be equivalent to D. So this this is a new condition. So you can, for each of these cells, wherever you want the equivalences, you put that. Now let us go and look at the excess. A on a 0 you produce 0, A on a 1 produces 1. Let us go and look at C. C on a 1 produces 0, and C on a 0 produces 0. So, it looks like for A and C on the 0 transition, if you have input 0, the output is 0, but when input is 1, A will produce an output of 1, C will produce an output of 0. This means A and C can never be equivalent. So, you put an X here. Similarly, you go and look at A and D. So, on 0 it produces 0, on 1 it produces 1, D on a 0 produces 1 and on a 1 it produces 0, which means A and D cannot be equivalent. You mark a X here. So, you keep marking all these X's wherever you know for sure that they cannot be equivalent by the definition of equivalence. The equivalence definition says their outputs must be the same and their next states must be equivalent. So, the outputs are not the same for A and C, A and D, A and F, A and H and so on. Now, what you have is what is called a implication table. Given the implication table, now we want to see whether we can minimize the number of states. From these 8 states, can I come to a different state machine which has lesser number of states. So, now let us go and look at each one of these in turn. So, I go and look at A, right. I go and look at A comma B. So, I go and look at A comma B, right. Then for A to be equivalent to B, H should be equivalent to F. So, let me go and check H versus F equivalence. From this table I already know that H is not equivalent to F. So, if H is not going to be equivalent to F, then A is never going to be equivalent to B. So, I cross that. So, this also becomes an X. A is not going to be equivalent to B. Then let us check this. For A to be equivalent to E, H should be equivalent to C. So, let us go and check H versus C. H versus C is a X. So, this is also not going to be possible. Let us go and look at the last one. For A to be equivalent to H, A should be equivalent to H itself. So, that is a redundant statement, but G should be equivalent to D, right. So, I go and look at the column G versus D. So, it is not a, so we have not resolved whether G and D are equivalent yet. So, I will leave this now. I will go to the next column. The next column I look at, I am trying to see whether E and B could be equivalent. For E to be equivalent to B, F should be, so let me go one step back. For E to be equivalent to B, F should be equivalent to C. So, let me look at F comma C. So, F comma C is a cross. So, that is not true. Then if I want H to be equivalent to B, then A should be equivalent to F, which we already know is not true. So, this is not possible also. This column says C is not equivalent to anything, right. So, this is not equivalent to anything. You know that from this column C is not equivalent to anything, and from this row also C is not equivalent to A and B either. So, C is not equivalent to any state at all. Let us look at this column. We want to check whether F is equivalent to D. If F should be equivalent to D, B should be equivalent to E. So, I go and look at B comma E. I already know that B is not equivalent to E, so I cross that. Then if I want D and G to be equivalent, B should be equivalent to B, that is trivially true, and D should be equivalent to G, and that is also, so if D and G is equivalent, then D and G is equivalent. So, this is actually seems to be correct. So, we will keep that. So, at this point we have established that D and G are actually equivalent to each other. There is no precondition required anymore. Let us look at this one, H versus E. Can H be equivalent to E? For H to be equivalent to E, A should be equivalent to C, which I know is not possible, so I will cross that. Finally, if I want to look at G to be equivalent to F, I want E to be equivalent to B, so I will go and look at B column and E row. I know that is not true, so this is also not true. So, what we have done is we needed several preconditions to be true, so that the row and column, so for every cell the corresponding row and column, if they have to be equivalent to each other, then the preconditions specified in the cell have to be satisfied, but it is not getting satisfied. Now, let us go and look at the table once more. B is equivalent to B and D is equivalent to G, which means there is no precondition anymore. B is equivalent to B is trivially true. For D and G to be equivalent, I want D and G to be equivalent. So, that is a tautology, it is always true. Now, let us come back and look at this. For A and H to be equivalent, A and H should be equivalent, it is trivial. So by default you get that, but you also want D to be equivalent to G. We just established that D is actually equivalent to G. So overall what we get is A is equivalent to H and D is equivalent to G. So now instead of 8 different states here, I can replace that with a states with a diagram of 6 states. So A is equivalent to H and D is equivalent to G. So from this state diagram you can go and reduce the state diagram. This potentially reduces the number of state. So in this case it went from 8 states to 6 states, which means it is going to remain at 3 flip flops. However, the combinational logic for next state and the output logic may actually reduce. I want you to do this as an example. So I give you this state machine. This is again having 8 states, and there is this on x equal to 1 you go to these, on x equal to 0 you go to these. In this case the output is not on x equal to 1 or x equal to 0. The output is defined based on the state, which means this is a Moore machine. So on a Moore machine what happens is, so the previous example was a Mealy machine, this is a Moore machine. If I want to find out equivalences for a Moore machine, then a state which produces a 0 cannot be equivalent to a state which produces a 1. So by looking at this I can say that A cannot be equivalent to C, E, F or H, B cannot be equivalent to C, E, F or H, and so on. I can do this. So what I want you to do is draw an implicant table. On the x axis you should start from state A, go to G. On the y axis you start from B, go to H, and you put all the crosses where you know that the output of the states are actually different. So A and C have different outputs, so A cannot be equivalent to C. A and G are different outputs, sorry, A and E are different outputs, A cannot be equivalent to E, and so on. And whenever the outputs are equivalent, then you need preconditions. If A has to be equivalent to B, you already know that the outputs are 0, so output is not going to pose a problem. However, for A to be equivalent to B, the preconditions must be C should be equivalent to H and D should be equivalent to F. You put those preconditions and I want you to go and solve this. So you have 8 states, go and find out how many states you want for this one. I will leave this as a homework problem, and this brings me to the end of this lecture module. So what we did in this lecture module is we started with the notion of a state machine, and we wanted to see if we can derive another state machine which has fewer states. The examples I showed you still uses the same number of flip flops, but it is quite likely that if you are not careful about your state machine, you end up with a very complicated machine with a lot of states, but many of which are redundant. You want to go back and change it to a state which has much simpler things. In fact, I would like you to go and try this on the tail light state machine also and see if you can reduce the states or not. So it had so many states, right? It had 3 states for the left side, 3 states for the right side, 1 for idle and 1 for the hazard. There were 8 states. Can you go and see whether it can be reduced to whether the number of states can be reduced even by 1? Go and check whether it is possible. So if you start with a state machine and if you cannot reduce the number of states even by 1 state, then that state machine is called irredundant. There is no redundancy in the state machine. Every single state is important, every single transition is important. You cannot get rid of any of the states. So that is the meaning for an irredundant state machine. But if there is redundancy, you want to remove it so that the hardware becomes simpler. Lesser flip flops means lesser logic and whatnot. So you want to reduce the number of flip flops. Equivalently, the number of gates in the input logic and the number of gates in the output logic may also reduce. So I have given several pieces of homework. I suggest that you go back and look at this and solve these problems for yourself. So thank you, and I will see you in the next module, module 32. In module 32, we will look at what is called state assignment. So state assignment is also important. So far we have been using symbols A, B, C and so on. I want to talk about state assignment in the next module. So thank you, and I will see you in a little while.